Welcome to this concluding presentation from the series Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams, a retired Associate Professor of Electrical Engineering. In this presentation, you will see some examples of historic solid-state devices. We hope that the dazzling progress in solid-state technology will be apparent in the following images to gain an appreciation for the talent, energy, and genius that have propelled solid-state electronics to the very center of daily life in the 21st century. The next few slides contain definitions of some terms that will be used in this presentation. We will go through them slowly to give you an opportunity to read them. First, the semiconductor. And N-type semiconductor. P-type semiconductor. Junction. And finally, diode. Bipolar junction transistor, or BJT. Metal oxide semiconductor field effect transistor, MOSFET, or sometimes just FET. Erasable, programmable, read-only memory, or EEPROM. An integrated circuit, or IC. Complementary symmetry metal oxide semiconductor, or CMOS. A microprocessor. Microcontroller. And finally, Moore's law. The first solid-state devices that were used in practice were crystal rectifiers. A rectifier is a junction between two dissimilar metals or materials that permits electric current to pass in only one direction. These junctions were early solid-state diodes. Metal crystal rectifiers were employed as detectors in radio circuits. In this example, the crystal is galena, which is lead sulfide, and a wire called a cat's whisker could be adjusted to touch the crystal in various places until a rectifying place was found. This is an example of a commercial silicon carbide detector or rectifier from 1911. But these primitive devices were just at the beginning. Later development of diodes greatly extended their ranges of applications. This is a selenium rectifier stack for AC to DC power supply applications. They were introduced in the 1930s and were more efficient than vacuum tube diode rectifiers. This rectifier stack is capable of carrying a current of 450 milliamperes when conducting and withstanding 160 volts when not conducting. This is a photograph of some modern diodes, including an MBD 701 diode using a metal silicon junction called a Schottky barrier, a 1N4001, which is a 100 volt 1 amp silicon rectifier diode, 1N4148 general purpose diodes, a 6A1 100 volt 6 amp silicon rectifier diode, and this last one is a 400 volt 1 amp rectifier from the late 1960s. And when I found it, it was still in its original packaging, on which the price said 59 cents. But the diode couldn't amplify. Then these three men invented the transistor and forever changed the world. Their work earned the Nobel Prize for Physics in 1956, John Bardeen left Bell Laboratories for academia, where his work in superconductivity earned him a second Nobel Prize. Walter Brattain retired from Bell Laboratories. William Shockley returned to his native California with hopes of making money from semiconductors. Shockley hired talented people and brought them to Northern California, but management and personality disputes led 8 of them, called the Traitorous 8, to leave Shockley and start a rival company sponsored by Fairchild Camera and Instrument Company. People branched out from Fairchild to launch many other ventures, including, you may have heard of this one, a small company called Intel. Anyway, this was the origin of Silicon Valley. The first transistor that was made available to the general public was the Raytheon CK722. This is the original packaging of the CK722, and this is the CK722 inside its packaging. The same paper envelope package was apparently used for other devices because you can see here diodes as well as transistors. This is a close-up of the CK722. This was a germanium device made of one layer of N-type material between 2 layers of P-type semiconductor material. This structure was known as a PNP transistor. The 3 terminals are called the emitter, base, and collector. The base was the N-type layer, and the emitter was marked with a red dot. The transistor radio was one of the first commercial applications of the transistor. This is a photograph of the Regeney TRI, the world's first transistor radio. This is its schematic diagram. Don't worry if you can't decipher much from it at this point. At the time you graduate, it'll make a lot more sense. It was jointly developed by Texas Instruments and IDEA of Indiana, and it was a vehicle for selling Texas Instrument transistors. The TR1 used 4 NPN transistors, designated here on the schematic, and 1 diode. IDEA first marketed the TR1 through its Regency division in November of 1954. Sony entered the transistor radio market in 1955 with its TR55. The Sony TR63 was introduced to the US market in 1957, and the manufacture of transistor radios rapidly shifted overseas. These are examples of transistors from the 1960s. There were various packaging styles, including molded plastic, metal cans, etc. One transistor was functionally equivalent to 1 vacuum tube triode. So 2 transistors were the equivalent to this 12AT7 twin triode shown for comparison. Germanium was an early favorite semiconductor material, but it was rapidly displaced by silicon in the 1960s. Here we have a pair of GP1291 germanium power transistors from the late 1960s in these so-called TO3 packages that were used for applications involving significant power dissipation. Their packaging allowed them to be readily connected to a heat sink for additional power dissipation capability. Germanium transistors were commonly used in the output stages of audio amplifiers, particularly in low voltage applications like 12-volt automotive electronic applications. Germanium transistors are still available for replacement purposes, but germanium is no longer used as a material for new transistor designs. The transistor ushered in a revolution, but there was another revolution brewing. This image is from the patent application from Jack Kilby's work in the summer of 1958. His idea was to integrate an entire circuit on a single bar of germanium. Kilby had a prolific career at Texas Instruments, including the invention of the handheld calculator, and he earned a share of the Nobel Prize in Physics in 2000 for his invention of the integrated circuit. At the same time, Robert Noyce at Fairchild was pursuing similar ideas. This image is from Noyce's patent application for what's called a planar IC, where everything was built on a plane, a flat surface on a bar of silicon. All of the elements, circuit elements, were isolated through what's called junction isolation. Notice the substrate here is P-type material, but all circuit elements in contact with that are N-type regions. This junction isolates circuit elements from the substrate in each other by taking advantage of the rectifying properties of P-N junctions. Noyce was one of Shockley's traitorous 8, and he was later a founder of Intel. Kilby and Noyce are recognized as co-inventors of the integrated circuit, although Noyce had died before Kilby was recognized with the Nobel Prize. As integrated circuits began to move into commercial and industrial applications, the dual-inline package became the leading packaging type. The chip had a lead frame were enclosed in either a molded plastic enclosure or a two-piece ceramic package. It was a popular packaging style from the 1970s onward. These chips had 2 rows of pins. In each row, the pins were spaced at a distance of 1/10 of an inch, and the 2 rows were separated by a space of 3/10 of an inch, although there were some wider packages manufactured. The devices shown here are linear integrated circuits like operational amplifiers and small-scale digital integrated circuits like arrays of logic gates. Surface mount packages began to compete with DIPs in the 1980s. These devices are soldered directly to the traces of a printed circuit board and allowed much more compact construction than DIPs. Most DIPs had 8, 14, or 16 pins, but there were exceptions. The ADC0804 analog to digital converter shown here is packaged in a 20-pin plastic dip. And there were other packaging styles as well, shown by this LH0032 high-speed amplifier in a 12-pin circular package. This style was called a TO8. Now let's take a look at the state of the art in digital logic devices at the end of the 1960s. The dominant type of logic circuits at the time were called TTL, meaning transistor logic. This is a diagram of a 2-input NAND gate. Circuits were composed of transistors, resistors, and diodes. TTL operated with a 5-volt power supply and used positive logic. A low output voltage represents a logic 0. A high output voltage represents a logic 1. TTL was the technology that took astronauts to the moon in 1969. But TTL had significant drawbacks. The resistors took up far more chip area than the transistors, and they were the source of significant power dissipation. These would have prevented the microprocessor revolution of the 1970s, which was made possible by the development of a new type transistor. In the late 1960s, a new type of transistor began to appear in designs. The metal oxide semiconductor field effect transistor, MOSFET, sometimes, as I said earlier, shortened to FET. As the MOSFET became more widely used, the original transistor was renamed junction transistor or bipolar junction transistor, BJT, to distinguish it from the FET. An equivalent 2-input NAND gate implemented with NMOS and PMOS transistors is shown here. The designation PMOS or NMOS depends upon the details of the construction of these devices. Note that only MOSFETs are used, no resistors. This type of logic using both PMOS and NMOS transistors is called complementary symmetry, MOS logic, or CMOS. Unlike the TTL NAND gate, this CMOS gate has no static power dissipation. It only dissipates power when it's switching states, when the output is switching between a 1 and a 0 or vice versa. The low-level output voltage of this gate was 0 volts, and the high-level output voltage was equal to the positive supply rail, which was 3 volts to 18 volts. Engineers could design with CMOS logic after RCA introduced the CD4000 series of digital devices in 1968. CMOS became very popular and numerous other vendors entered the market, and CMOS technology dominates digital design today. One place in which MOSFET technology first made its mark was in engineering calculation. The slide rule, a form of analog computational device based on the addition and subtraction of logarithms, was the standard calculating device for engineers and scientists from the 19th century to the early 1970s. The introduction of the handheld calculator in 1972 displaced the slide rule. The world's first scientific calculator was the HP 35. The HP 35 used what was known as reverse Polish notation for entering calculations. This is a method in which two operands are entered, followed by the operation, rather than operand, operation, operand equals. This method is more efficient than algebraic entry, and it's still standard on Hewlett-Packard calculators. Here we have the Texas Instruments SR50, the first Texas Instruments scientific calculator. Interestingly, the SR stood for slide rule. Both of these calculators were still functional when this photograph was taken in December of 2019. An extension of standard MOS technology made possible the non-volatile memory chip, one that retains its data without an external supply voltage. This was useful for dedicated systems that did not require loading new programs, something you could program once and just leave. These devices were known as erasable, programmable, read-only memories, or EPROMs. The programming was accomplished electrically, but erasure was accomplished by means of ultraviolet light. That's why the devices were housed in ceramic packages with windows that were transparent to ultraviolet. In this lineup here, we have a 1702, which was arranged as 256 8-bit words introduced in 1971. This was the world's first EPROM. The square that you see visible in the window is the actual device itself. The rest of this is packaging and lead frame. We have a 2716, which was arranged as a 2K by 8 EPROM in a 24-pin ceramic package introduced 1977. And we have a 2732, which was 4K by 8 EPROM in a 28-pin package, 28-pin ceramic package introduced in 1979. And EPROM technology was applied to other devices that contained programmed memory as well, not simply just memory chips. For example, we have the Intel 8741 Universal Programmable Interface, an 8748 microcontroller, an 8755, which combined a 2K by 8 EPROM with 2 addressable I/O ports. And just for comparison, we'll include here an Atmel microcontroller from 2004. The program of this device is stored in electrically erasable programmable read-only memory, or EEPROM, which is also known as flash memory. Flash memory has superseded the EEPROM. Now, let's look at some examples of advanced microprocessors from the 1980s. We have a photo of 2 different microprocessors using 2 very different packaging styles. The Philips ADC552 8-bit microprocessor with a built-in analog to digital converter and pulse width modulated outputs mounted in a 68-pin quad flat pack, 17 pins on each side. The larger chip at the bottom is a MOSTEC 68000P, a 32-bit microprocessor unit in a 64-pin ceramic dip. So let's look at some 1990s era processors. These are in the X486 family. Here we have an Intel 80486 32-bit microprocessor unit. The bottom side of the 8486 shows the array of 168 pins. Here we have the Intel 486DX, which had 1.2 times 10 to the 6, or 1.2 million transistors, with a minimum feature size of 1 micrometer, introduced 1989. We have the Intel 486SX, which had 1.2 times 10 to the 6 transistors with 1 micrometer feature size and 900,000 transistors of 0.8 micrometers, introduced in 1991. And lastly, we have a Cyrix CX486, which ran at a clock speed of 66 megahertz. Let's take a look at the Intel Pentium Pro. This is a multi-chip module with both an MPU and a cache memory in a ceramic package. This chip had a 256 KB cache memory. Other cache sizes were available. It was introduced in 1995, had 5.5 million MOS transistors with a minimum size of 600 nanometers. For comparison, green light has a wavelength of 660 nanometers. Gives you an idea of how small these transistors were. It was superseded by the Pentium 2 Xeon in 1998, and the multi-chip module had a total of 387 pins. Now, from the CK722 to the Pentium Pro required only 40 years, about the working lifetime of one engineer. This should, I hope, convey a sense of the dynamic changes that the solid-state revolution brought to electronics. One indicator of progress in electronics is Moore's Law. First published by Gordon Moore, one of the founders of Intel in 1965. He said that dense ICs like MPUs and memories will double their transistor counts approximately every 2 years. It has been remarkably predictive for the last 5 decades. Let's look at some numbers for comparison. Here we have the world's first microprocessor, the Intel 4004, which used 2,250 PMOS transistors. And compare that with the Intel Xeon Broadwell E5 from 2016, a CMOS device that used 7.2 billion transistors, introduced only 45 years later. And look at the feature size, a 10 micrometer feature size in the Intel 4004. 45 years later, 14 nanometers. Now, I'd like to make a little personal detour. This was a project that I did at the University of Illinois in 1973. The University of Illinois offered an undergraduate course in solid-state devices, including a fabrication laboratory where devices could be constructed. Each student was given a small piece of silicon to work with, and we worked with that piece of silicon for most of the semester. We built devices, actual microelectronic devices, on our silicon wafers. We followed that with electrical test and characterization, and the chip actually contained working devices. Among the other working devices here are a MOSFET, a diode. Here we have some MOS capacitors and a bipolar junction transistor. So let's sum it all up. Approximately 70 years elapsed from this primitive vacuum tube to the Intel Pentium Pro. This progress required the application of new physics, new understandings of material science, incredible advances in manufacturing technology, and just sheer ingenuity. Electronics is a story of dreams, of fortunes, of new technologies, and of technologies superseded by newer technologies. It is also a story of human ego and vanity, incredible social change. So, some parting thoughts. Welcome to a fascinating, challenging, and dynamic profession. You'll do great things as you stand on the shoulders of the giants who have come before you. We hope you've been inspired in seeing some of their accomplishments. Thank you for watching.